Okay, Mr. Jones here. Chemistry. This will be the notes for pages 65 through 68. So starting a new unit in a new semester. This unit's going to be focused on acids and bases. And I've referred to it a few times in first semester, and I've put a few things off saying, well, we'll deal with that when we get to acids and bases. And we're here now. There's a lot of equilibrium involved because of the weak ones. Let's see. And one of the most important labs in all of chemistry is in this section. And of course, that's titrations. But first, let's look at a new sig fig rule. So it turns out there are many more rules for sig figs than what we typically cover. I'm just going to cover one, and I'm going to do a simplified version. So anytime you do logarithms, whether it's a regular base 10 log or a natural log, if you are taking the log, I want you to add one sig fig. So for example, if we were to calculate the pH in which a solution had a 2 times 10 to the negative 5 molarity, we would take the negative log of the hydrogen ion molarity. And normally, if you kept 3 sig figs, you would get 4 point, in this case, 70. But I want you to add one more sig fig. So in this case, you should get 4.699. And you should practice this. Just make sure you remember how to do this in your calculator. Likewise, if you take the negative log of 1.0 times 10 to the negative 5, don't just write 5.0, add one more sig fig so you get 5.00. Now, when doing the opposite, when you are undoing a logarithm or inverse log, we need to undo what we already did before. And so now you need to take one sig fig away. So if you were given a pH of 2.77, to remind you, the way you get the hydrogen ion is you do hydrogen equals 10 to the negative pH. So in this problem here, you would take 10 and raise it to the negative 2.77. And when you do this, depending on your calculator, you'll either hit second log or something like that. You can refer to this as an inverse log, or you can refer to it the way I have mathematically as the number 10 raised to the negative pH. And you end up getting 1.7 times 10 to the 3 molarity. And I took one sig fig away, which is why I went from 3 sig figs to 1. Be careful. I'm reminding you, pH doesn't have units, but molarity, or concentration rather, has units of molarity. So be careful there. Sometimes in this unit, people get used to talking about pH so much, and they get used to there not being any units. They get in the habit of not putting units, and when there is a concentration, they forget to put molarity. Another one here, we start with 5 sig figs, so my answer has 4 sig figs. Now I see my note in red here to discuss where pH comes from. The history, as I understand it, is it comes from a Danish guy named Søren Sørensen. And he did a variety of things. And one of the things he did was he made beer. And apparently when you make beer, you need to monitor the acid level, otherwise it doesn't turn out right. And he got tired of writing numbers like this. So he was probably keeping some sort of notebook, and he kept writing numbers like 1 times 10 to the negative 5 molarity or something like that. And that was getting tedious. And he decided, I want to shorten it and make it, I want to say the same thing, but in a shorthand version. Well, he knew he could get rid of the exponent if he took a log. So in this particular case, it gives you negative 5. But nobody really wants to deal with negative numbers, so he's like, oh, well, then I'll put a negative in front. So the negative log gives you something like 5. And it was a lot easier for him to write 5 in his notebook. In other words, pH is 5, as opposed to writing the hydrogen ion concentration is 1 times 10 to the negative 5 molarity. They both say the exact same thing. A pH of 5 and a hydrogen ion concentration of 10 to the negative 5 molarity are the exact same thing. This is just a shorthand version. So it doesn't tell us anything new. It just tells us the same thing in a new way. And he decided to use the pH because he was taking the power of the hydrogen ion. So a symbol for that made sense, was that he would do power of hydrogen. So that's what pH is. Okay, moving along, I saw this picture a few years ago on the internet and thought it was interesting, not just because whoever made it did a decent job with their artwork, but they didn't do such a good job with their chemistry. And you'll see I've crossed a bunch of things out. A lot of what it says is correct, but there are a few errors in it. And so I just wanted to make sure people were aware that there are errors. You don't need to take the time to go through them. If we have free time in class, we can go through it just for fun. Down here, I mention that the proper rule for the sig figs is a bit more complicated than what I mentioned above, but we don't need to worry about that. We're taking a simplified approach to the new sig fig rules, but this is the correct rule down here, and you're welcome to use that if you want, but I typically don't bother in our class. All right, get into some of the details. There's going to be a lot of just minutia that we have to get through in this lesson. So it might take you a couple times going through it to absorb everything. So we'll start with some terms. If an acid only gives off one hydrogen, it is said to be monoprotic. If it can give off two, it doesn't mean it is gonna always give off two, it just has the ability, it is diprotic, and if it can give off three, it is triprotic. I've never heard of anything being higher than that, although it may exist. Now notice, this doesn't mean it has three hydrogens. It means it can give three of them off. So it needs to have them and it needs to be able to release them as hydrogen ions. So for example, something like CH4, it has four hydrogens, but it is not triprotic or diprotic or monoprotic or quadriprotic. It's not an, so it's not about having hydrogens, it's about the ability to give off an H plus. And how many? Sometimes people refer to the ones that give off more than one as polyprotic. So just some terms to be aware of. It's not a really big deal. These are some classic examples, by the way. A very common diprotic is sulfuric acid. And a very common triprotic is phosphoric. All right, strong acids. You learn in first year that the strong acids completely break into ions. The word we use is ionize because there were no ions before, but now there are ions. And since they completely do it, we use a single arrow. Now this statement we will keep using, but it is not entirely true. In many concentrations, they do completely form ions, but in certain scenarios, they don't. So for example, really concentrated acids, like if you take fully concentrated hydrochloric acid, that's going to be 12.1 molarity. It doesn't completely split. There's not enough water. It's kind of like you can think of the HCl ions as being saturated, and there's not enough water to allow them all to completely split. They still split most of the way, but not 100%. But we're just going to assume that they always split 100% just for simplicity. You should have memorized there are 6 of them. I've never heard of a really good way to memorize this. You just kind of have to do it. I usually group these three together because they're all in the same column on the periodic table and in order. And then the other three are just kind of random: sulfuric, nitric, and perchloric. One thing to notice is that one thing that makes them a strong acid is that the hydrogen is bonded to a highly electronegative ion. And so what that means is the highly electronegative other ion is able to take all the electrons, leaving you with just an H+, which is essentially the same thing as a proton. H+ does not have any electrons, and unless it's a heavy isotope of hydrogen, it doesn't have any neutrons either. So you'll see things referred to as H+, or you'll see them referred to as a proton, and that's saying the same thing. Now, I made this chart to kind of organize where most of the acids lie. But before I do the chart, let's talk about weak acids. Weak acids only partially ionize. So we're going to use a double arrow, and this is where we're going to have to do equilibrium calculations to figure out what's going on. And as I mentioned, most of them don't ionize very much. They, for the most part, don't split much at all. It's generally less than 5%. And in many cases, it's way less than 5%. So back to the chart, we can think of our strong acids as 100% ionizing. Most of your weak acids are going to be in here. Almost every single problem we do, they don't split that much. So they're somewhere less than 5%. There are a few that fall above 5%, but it's rare area. And then, of course, at 0% ionizing, that's not even an acid. So we're pretty much going to be focusing on this strong acid box and this weak acid circle on my chart here. Okay, because the weak acids don't split very much, your original concentration of hydrogen bonded to the other atom or polyatomic or whatever it happens to be is going to always be greater than the concentration of H+ that's given off. Now I'm going to go through some types of weak acids. This is going to take a little practice on your part to get familiar with these. Everything this unit is aqueous, so we don't really need to put states. So last unit when we did precipitates, the whole point was a change of state. Is it forming a precipitate or is it not forming a precipitate? So it was important to put those, but now everything's aqueous, so you don't really have to put the aqueous this unit. The one exception would be if we're dissolving something like a strong base in water, you might say it starts out as a solid, but it's not really important to what we're doing in most problems. So you'll see in the notes, I have left off the aqueous just to keep things a bit cleaner. So I've got types of weak acids. So molecular, in other words, molecules, covalently bonded atoms that give off an H+. So here I have what you would commonly know as vinegar. We will call it acetic acid. It gives off an H+, and you're left with an acetate ion here called a conjugate base. We'll cover that more later. It turns out acid-base indicators, those things that change color, whether you put them in an acid or a base or you change their pH significantly, they are also molecular acids. And you will see this, we'll cover this in more detail later on, but you'll see it written like this, where the actual molecule is very complicated, and we don't want to take the time to write out all the atoms and complicated formulas. So we'll just abbreviate it as HIN and IN-, in which case that is the version that has the hydrogen attached, which would be in highly acidic solutions. And then this would be the version in which the hydrogen has separated, and this would be in basic solutions, depending on the indicator though. So what I just said is a little bit too general, and we'll cover that in more detail later. A second type are negative ions that happen to have a hydrogen that can leave. So I have one here and one here. H2PO4 minus 1, known as dihydrogen phosphate, it is a negative ion, also has the ability in the right to give off an H+, so that makes it have the ability to be an acid. Likewise, HPO4 minus 2, it's also a negative ion, and it also can lose that hydrogen in the right circumstances, and so on. And I made a note here that if you're ever asked to explain this or show this, I recommend you show them in separate steps. Don't take both of these hydrogens off at the same time. Or if you're starting with the very top here, phosphoric acid, don't take all three off at the same time. It's because each of these would have a different equilibrium constant, and it's best to keep them separate. And here's another example. I say write the complete ionization for sulfuric acid. Okay, well, H2SO4 is a strong acid, so single arrow, gives off H+, and now you have hydrogen sulfate. However, hydrogen sulfate also has the ability to be an acid, so you can take your hydrogen sulfate, but it's weak, so double arrow, take off a hydrogen, and now you're left with sulfate, which doesn't have the ability to be an acid. So we've done two types. There's going to be a third type right here. It turns out that some positive ions, when they become hydrated, in other words, when they are put in water, some water molecules attach to them, forming a complex ion. So we talked about this last unit, if I remember right, the very last lesson, in a way that you can dissolve precipitates is by forming a complex ion. Well, this is also an example of a complex ion, but we're not dissolving precipitates necessarily. So take this first scenario. Zinc chloride, if you put it in water, it splits, because it's ionic, it splits into zinc and chloride ions. And that's not the point here, I'm just referencing that that has already happened. In the water, the zinc ion will grab 4 waters and attach them to it, forming this complex ion. So this here is the complex ion with 4 waters attached to the zinc. Notice the charge doesn't change because zinc is +2, water's neutral, so you end up with a +2 in the end. Now, in this third step right here is where you're going to see it being acidic. So the first 2 equations are just prep. It turns out this zinc with 4 waters +2 complex ion, it has the ability to give off a hydrogen. One of the hydrogens of one of the waters can come off. So you see that there. And notice what's left. We still have the zinc. We still have 3 waters, but one of the waters has lost an H. And so all that's left is OH. And notice the charge of the entire complex ion has changed. If you lose a +1, that means you have to go down, in this case, from +2 to +1. You can also think of it as if you lose a +1, you have to become 1 step negative. Well, 1 step negative from +2 is +1. So this here is also a complex ion. So there are 2 complex ions, but the one that I'm focusing on right now is the one that's acidic. It's this one here. We don't really have to go through the naming of these things, but there is a naming system for the complex ions. I'd have to review it. I think this one, the one that I've circled here, would be something like zinc tetra aqua 2, as in a Roman numeral 2. Something like that is how they name it. They usually make sense. If you see the name written, you'll probably understand what to do, but you don't have to worry about naming them yourselves. Now, notice I have this phrase, double the ligands. Ligands are the attachments. In this case, the ligand is the water. And you always want to put double what the charge is. So because the zinc was a +2, we need to add 4 ligands. Now there are different ligands that can attach, but right now the only ligand we are going to worry about is going to be water, because we're focusing on this situation of weak acids. Note up here, group 1 and calcium, strontium, and barium do not do this. It's because they are the result of a strong base, and so this wouldn't make sense to do it this way. But all other cations have the ability to do this. So things like zinc and iron, magnesium, and so on can do this. All right. Here's another example. It says, show how a solution of iron 3 chloride can be acidic. Well, at first, if you just look at iron 3 chloride, that doesn't look acidic at all. It looks like a typical ionic compound, but it can be once you start looking more detail. So again, I'm just showing the fact that iron chloride in water forms iron and chloride. It's only the iron we care about. So you take the iron like I have here, double the ligands. So since it's +3, I'm going to add 6 waters. That forms this complex ion here. We still haven't shown it being acidic. All I've done so far is formed the complex ion, and the real point of the problem is happening here in the third equation. I take the complex ion, it's weak, so double arrow, take off a hydrogen, and then notice I lose one of my waters, it becomes OH. I keep 5 of the waters, and the charge goes from +3 to +2. So really, showing how FeCl3 can be classified as acidic is being shown in the third equation. If this were a test, I would ask that you show me these 2 equations. I want to see the formation of the complex ion and then the complex ion being acidic. You don't need to show this first equation, so if you want to just skip that, that's fine. I'm just showing it to be complete. All right, that was the acids. Now we got to do the bases. All right, strong bases. Again, we assume that they completely split. Notice the word is different. In this time, I'm not going to use the word ionize. I'm going to use the word dissociate. And the reason is because they already exist as ions. We are not creating ions. They're ionic already, the compounds, and they're just splitting when you put them in water. So it's group 1 and calcium, strontium, and barium hydroxide. So like sodium hydroxide, calcium hydroxide, and so on. A lot of people learn this on the periodic table as group 1 and senior Baca. It helps them remember those 3 are part of the strong bases. And I have an example of that happening here with sodium hydroxide. All other bases are weak, so we say that they partially dissociate. And there coincidentally are going to be 3 categories again. Just like in the weak acids, we had 3 categories, we have 3 again. We have all the other hydroxides, so magnesium hydroxide, aluminum hydroxide, iron hydroxide, tin hydroxide, things like that. There are some molecular ones. One is ammonia. And ammonia is a tricky one. When you look at ammonia by itself, it looks like it would be an acid. You see those 3 hydrogens and you think, oh, it's going to give off hydrogen, but it doesn't. It doesn't give off those hydrogens, so it's not an acid. In fact, it does the opposite. It gains a hydrogen to become ammonium, so it is a base. You just need to know that one. You just need to know that NH3 is called ammonia and it is a weak base. Another group, and this goes to organic chemistry, are called amines. I've heard it pronounced amines and amines, so I guess it depends on who you're talking to. And these are organic molecules that have a nitrogen component or an amine component. R refers to the rest of the molecule. And that would be some sort of hydrocarbon. So just as a random example, it could be something like CH3, CH2, CH2, NH2, something like that, in which we just have random organic stuff with a nitrogen component. These also are weak molecular bases, just like ammonia. They give off hydrogen. You can even think of ammonia as being related to this, and the organic part is just another hydrogen. And if we wanted to show that, we don't really want to get into all the details of the organic molecules right now. So we would just keep the R, show that it gains a hydrogen, so it becomes NH3. And just like ammonia becoming ammonium, it becomes a +1 ion. Now, again, when you look at these, this doesn't look like a base, and this doesn't look like a base. But notice when you put them in water, water gives them a hydrogen, and what's left is a hydroxide. So they are indirectly making hydroxide. Now they look like a base. And the third category are negative ions. And the reason negative ions can be a weak base is because they have the ability to gain a hydrogen, just like we saw with the ammonia and the amines. Take F-1. Used in water, it has the ability to take a hydrogen, forming HF and leaving a hydroxide here. And of course, don't forget double arrows for the weak ones. So one thing that might help you is to notice of the weak acids, there were 3 categories: molecular, anions, and cations. In the weak bases, likewise, there were 3 categories: molecular, anions, and then the other hydroxides. So that might help you with learning this. It's going to take you a few days to get used to all this stuff. This is a lot of information. All right. The models. So it turns out one of the, I guess I should say, annoying things about acids and bases is that there are really 4 definitions or models. The first definition came from a long time ago. So the very first one is simply how they taste. And people noticed that there were certain things that had a sour taste: lemons, oranges, limes, and so on. And that was the first definition. An acid was sour. Now, of course, that's not good enough because it doesn't have any numbers that go with it. It doesn't say why they're an acid. And we wouldn't want to go around tasting everything in the lab. So that was just a very early way of getting this started. Then along came Arrhenius. His name is Svante August Arrhenius from Sweden. He said acids contain an H+, or even better, acids give off an H+, and bases contain or give off an OH-. And this is a point It's fairly simple. Acids give off H plus, bases give off OH minus. However, it doesn't always work. So like it says here, it's good for water solutions and it's good for certain scenarios, but it doesn't cover them all. So then along came a guy named Bronsted and another one named Lowry that worked together. It's two different people. And they modified this a little and they said protons. Remember, proton and H plus is the same thing, and bases accept them. So their version of acid was pretty much the same as Arrhenius, but bases, they took a different approach. And so if we look at this example, this bicarbonate, hydrogen carbonate, if you want to call it that, and water, these two things, they can both be an acid or a base, depending on what they're in. So if I just gave you this and didn't give you any more information, you might not be able to tell which one's an acid and which one's a base. But if I tell you what they do with this equation, you can now see the water gave an H plus to become hydroxide, so it must have been the acid. The bicarbonate gained an H plus. You can see it's got two H's over here, so it must have been the base. Now, if you start out an acid, you become a conjugate base. Think of it as your alter ego. And if you start out as a base, you become a conjugate acid. So you always become the conjugate that is opposite of where you started. Sometimes you'll see this referred to as conjugate. Sometimes you'll see it referred to as conjugate acid base pairs. So for example, if a problem said, name a conjugate acid base pair in this example right here, you could say that HCO3 minus 1 and its alter ego, that is a conjugate acid base pair in which the first thing is the base and the second thing is the acid. I just have them in the opposite order of the words that I used. Now, this is what most of you would have done in first year chemistry. You would have done Arrhenius, you would have done Bronsted and stopped there. It turns out there is a third and arguably the best definition. I guess it would be considered the fourth if you count the sour taste, but normally people don't even factor that in. And this is called Lewis, and this is named after the same guy as Lewis structures. So Gilbert Newton Lewis, he gets credit for this too. He said, and he is a completely different approach, acids accept electron pairs and bases donate them. So acids accept, bases donate. Notice this is the opposite direction of Bronsted-Lowry, and we're talking about electron pairs. It turns out the Arrhenius sometimes works, the Bronsted-Lowry works more of the time, but the Lewis always works. But it's a bit more complicated, so we usually don't use this version, but I will show you right now just so that things are complete. For example, take ammonia, which we know is a base, BF3, boron trifluoride, which at first you probably wouldn't know what it was, but it's got to be the other thing. It is going to form this right here, and the reason it's written like this, as opposed to not showing that electron pair, is it's just emphasizing the fact that the ammonia is donating or sharing an electron pair with the other molecule. And that's why they make a point of showing that pair of electrons right there. So here's ammonia with an extra pair of electrons. And of course, it's triangular planar shape. It is going to allow that pair of electrons to be, they say donate, but I kind of think of it more as a sharing. So that makes it the base. The boron trifluoride, if we go back to Lewis structures, this was one of the exceptions. Boron is okay with only 6 valence electrons. And that's the correct Lewis structure with 3 single bonds. But that doesn't mean it wouldn't be happy with more electrons. So in this case, this ammonia comes along and says, okay, you can borrow these 2 electrons, and they stick together. And this formula shows it. We don't spend a whole lot of time with the Lewis acids and bases. It's more that it's important that you just realize that there is this other definition. All right, I'm going to use this last example to show that sometimes you can use all the definitions. So given this, F minus and water, I want to know who's the acid, and then I want to go through each definition in reverse order. Let's show it with Lewis, let's show it with Bronsted, and show it with Arrhenius. Well, first, if you're ever going to do Lewis acid-base definition, you should draw Lewis structures. So I have a Lewis structure of an F minus 1 ion here. Lewis structure of water. The fact that it's bent is not relevant right now. And F minus is an anion. Anions are one of the weak base categories. So there's a good chance it's going to be our base. Water has no choice but the other thing. It's got to be the acid. And so what's going to happen here is the F minus 1 ion is going to share a pair of electrons. It would be this pair right here. It's going to share it, not with the entire water molecule, but with one of the hydrogens. So a hydrogen leaves the water, grabs onto this pair of electrons. I could have picked any of the 4 pairs. I just randomly picked that one, making this. The water, after losing the H plus, becomes hydroxide. If I asked for you to label it, this would be the conjugate acid. This would be the conjugate base. But that's really not being asked in this problem, so I'll just get rid of that. And so the way I've drawn it with Lewis structures, you can see how it fits the Lewis definition. Now, if we go to the Bronsted definition, the base is accepting a hydrogen. On the left, it doesn't have a hydrogen, and on the right, it does. The acid is donating a hydrogen. The water has 2 hydrogens here, but over here, it's only got 1. And if we do Arrhenius, the acid is giving off a hydrogen. It would be this one, according to my drawing. But again, you could have picked either one. So that makes sense. And you might think, well, it doesn't work for the base. The base is not giving off a hydroxide, but indirectly it is making a hydroxide over here. So it doesn't really fit the Arrhenius, but I suppose if you stretch it a little bit, you can say that it indirectly gave off a hydroxide. Now I like to ask this question, why does copper 2 chloride corrode the metal balance top? So on our balances, we have pretty good balances, and the top that you actually put stuff on is made of metal. And we do a lab in first year chemistry, it's lab number 3. And in the lab, one of the chemicals you have to weigh out is copper 2 chloride, solid. It's like a kind of an aquamarine, powdery or grainy solid. And of course, as you're doing the lab, you're not worried about the balances and you're just trying to figure out what's going on with the lab and so forth. And at the end of the day, if we have a balance, and we can look at the little metal top, at the end of the day, there's all these little pellets of spilled copper chloride all over the balance. After one period, it's not too bad, but after a few periods, it's usually covered pretty bad. Well, if I don't wipe that off and I just leave that there for a few days, it will start reacting with the metal pan and it will corrode it. And at first, it doesn't make any sense. You would think copper 2 chloride, it's ionic. Isn't it just going to sit there and do nothing? But it turns out this is a weak acid because as the solid particles sit there, the copper and the chloride absorb water. And then what happens is the copper ion gains to form the complex ion. And then, oh, I said I wasn't going to put states. And then this complex ion is acidic, and it reacts with the metal top, and that's what messes up the balance top. So you'll notice this actually. If you look at any of the balances, you'll see little pits, tiny, not really holes, but little dents from stuff like this just being spilled and sitting there long enough that it starts to react with the balances. Okay. I mentioned reading the chapters. You should always, this is just me reminding you, you should always read the chapters in the books at some point. I usually recommend on a weekend and so forth. And this finishes notes 65 through 68.